So here on page 8, we learned the basics of electron configuration. This is sometimes called complete configuration. This is the normal full configuration that labels every single electron in an atom, where it's at, what energy level, and what orbital shape it has. Now, as page 7 talked about, we have different shape orbitals, and each of those shaped orbitals corresponds to a different area of the periodic table. In the video where I kind of showed you the building of the atom, where all those different shaped orbitals got added in a certain order, well, we're going to add them in that specific order based on their location, the element's location in the periodic table. So there are 4 main blocks corresponding to those 4 main shapes. The S block, those spherical shaped orbitals, get added to the elements in the first 2 columns of the periodic table. Now it is a block, and this looks like a rectangle, even though if you look at your periodic table, it kind of has a little chunk out of that second column. It starts lower down. Well, that's because helium technically could and should fill in that second column of that periodic table. It's also an S block element. It's just over there at that far end of the periodic table for some other special reasons. Underneath helium is what we call the P block. Nice rectangle there, full of elements. The ditch of the element between the S and the P block is called the D block. And then down there, it looks like it's separate from the periodic table, is the F block. Now it's not really separate, and this is important here. Let me show you what the periodic table is supposed to look like real quick. This is what the true full periodic table looks like when it's all put together. We have our S block elements here, our P and our D, and then our F block are here between the S and the D block elements. And that bold line that you see at the bottom of your periodic table between the S and D, only in those bottom 2 rows, is supposed to kind of show you that that's where those F block elements get inserted. The only reason why they're separate is because this periodic table, in its true full form, is just so long and skinny. It doesn't fit very nicely on a piece of paper. So because we don't use these F block elements very much anyway, they take up a lot of space, then we pull them out, squish them to the bottom, and our S, D, and P all fit across a piece of paper a lot nicer. Now, something to write in your notes, something new, is that each of these areas has a different specific energy level that they start at. Each energy level basically can add a new shape of orbital. So our S elements, our S block elements start at 1 on energy level 1, P start at 2, D start at 3, and F start at 4. This is important because, as you see in your notes, you have a periodic table that already has a lot of labels in it and on it. And I want to help you understand where those come from, because your periodic table you use on tests and quizzes are not going to have those labels. So I'll give you a dry erase marker so you can add them, but you kind of have to understand what they are and where they belong to get there. So if you have a paper periodic table that you'd like to add these labels with me, I'd highly encourage you to do that. And I'll show me adding this with you in just a moment on a periodic table that looks just like yours. But when we say that S starts at 1, that means that the first row, top left block, or kind of row of the S block is called the 1s. P start at 2, so the top left square, the beginning of that P block, is what we call the 2p orbitals. D start at 3, so 3d there at the top left of our D block, and F start at 4, so 4f there, the top left of the F block. These are our starting points for all of these blocks. And as we go down each row, below the 1s is the 2s, then the 3s. We're technically going up in energy level, building up our atom into bigger and bigger spheres there as we go to higher and higher energy level, but they're all still spheres. Over there in the peanut shape, the P block, those peanut-shaped orbitals, 2p is the smallest P orbitals we have. Underneath it, we start adding a bigger and bigger third energy level, fourth energy level. They're still peanut-shaped, but they're bigger and bigger as we build our atom. As you might expect, underneath 3D is 4D, then 5D, 6D, and underneath 4F is 5F. So I would definitely recommend that you write these on your periodic table. This is one of the most helpful things to writing our electron configurations. Just start with those key labels: 1s, 2p, 3d, and 4f. And just like I did in that image, underneath 1s, let's just make those numbers bigger every time we go down a row. So we got 2s, then 3s, 4s, all the way down to 7s. And I know we have these number labels here, but I really think that it helps to see these as part of those elements so we can go through our elements. We can add underneath 3D, 4D, 5D, and 6D. Underneath 4F is 5F. And all we've got to do is come over here and finish out our P's. We've got all of the same labels that you need, or that you have on that little bitty periodic table in your notes. But this is going to help us so much, because what we're about to be doing, and I'll go back to that packet in a second and fill out a little bit more notes and explain stuff to you. If I'm getting to a specific element, if I want to write the electron configuration for something like nitrogen, what we need to do to write its configuration is go row by row across the periodic table, labeling what orbitals we hit, so kind of what areas we're going through, and how many squares we go through in that type of orbital, in that area, and put together a configuration. And we just keep going till we get to our element. So nitrogen, we'll write this out again in a second together. We always start at the top left. We always have to start at 1s. And since we're going through not just one, but two squares here, it's going to be 1s2. After we get to the end of a row, we go back to the beginning of the next row, where we see 2s. And since there's two squares here for us to go through, that's 2s2. You might say, oh, but miss, there's more squares that I need to go through to get to n. But those are actually 2p's. So those are a separate term that we need to go through. And we don't just stop at that first square or the second one. We have to go 3 squares in to get to nitrogen. So nitrogen's configuration is 1s2, 2s2, 2p3. If I was going to try and get down to one of these elements in the 5th row, I'd have to finish out all of those p's, get to the end of the 2nd row, go through the entire 3rd row, go through the entire 5th row, and then the 4th row, then the 5th row until I get to my element, naming every single type of orbital that we hit along the way and how many squares of that type we go through before we get to the next type, before we get to our element. So these can get rather lengthy, but if you have a map like this, a periodic table with those labels on it, then you've just got to take it carefully and go row by row, labeling where you're at and how far you need to go in each. Now, this is kind of like giving directions on how to get to an element's house. We're just going row by row, saying where we hit, how far we go, like turn onto Miles Road, go 2 blocks north, get to Zaxby High School. But what you've got to remember is that all of these terms, just like what we wrote back on page 7, and this is already on page 7, you don't have to write this here on page 8. Each of those big numbers represents the energy level that those electrons are on. The letter represents the shape of the orbital the electrons are in, and the little bitty exponent number, that superscript, represents the number of electrons in that orbital. So helium, its configuration is 1s2, and what that means is that it has 2 electrons in a spherical shaped orbital on the first energy level. So it's important we don't lose that meaning as we work through this analogy of treating the periodic table like a map and giving directions to our element. Now, this little note is already written in your packet. The Aufbau principle tells us to fill from lowest to highest energy. Number of electrons is the number of squares. The Aufbau principle means that we have to start at the lowest energy. We always have to start at 1s. Even though it's really basic, it's really simple, it's extremely repetitive, we've got to start at that 1s orbital every single time. So, let's do a couple of these configurations. I can't fit that whole periodic table on the screen while I'm still writing these configurations, so I'm just using that itty-bitty one like what you have at the top of your page, but since it doesn't have the element symbols there, I've gone ahead and highlighted those squares where our elements are. And these are some of the simplest, smallest elements. Hydrogen is H. It's right here at the beginning of our periodic table. And since that's where we start writing configurations, we just need to label that. That's 1s. And since it's in that first square there, that's going to be 1s1. To get to helium, which is that second square on the first row, that's still a 1s orbital, but since we have to go to the second square, we write 1s2. Note, we don't write 1s1, 1s2. We don't have to label every single square we pass through. Just like if I'm giving you directions, I don't have to say, turn onto Miles Road and go 1 block, and then go another block on Miles Road. If I need you to go 2 blocks, I'm just going to say, turn onto Miles Road and go 2 blocks. It's much simpler and more direct that way. So to get to lithium, we have to start at the beginning still. We always start at the beginning. But lithium is down there in the second row, but we still have to go through all of the first row before we can come down to the second row. So we start at 1s, and we still have to go through both of those squares before we're done with the first row. And then we can come across to the second row, which is the 2s orbitals. Since lithium is the first square in that section, then it ends at 2s1. So 1s2, 2s1. We got 2 terms here because we got 2 different types of orbitals here. Beryllium is right next to it. It's 2 squares in to that 2s. But we still have to start the same place with 1s. Go 2 squares over in that 1s, and then we can go to the 2s row, and we go 2 squares over there, and that will get us to beryllium. So hopefully you can kind of see this progression where this number is just increasing by 1, or we're adding a new term and increasing that by 1. Now in this next set of elements, we're going to start jumping around a little bit more, but we started with those simple elements to help you see that progression. Now I've already written out nitrogen once for you, but I want you to practice this the same way that we did. Nitrogen's down there in that second row. We've got to go all the way across the first row first and through the beginning of that second row before we can get all the way over to nitrogen. So we're going to start at 1s and go through 2 squares. Gets us to the end of the first row. Then at the beginning of the second row, we hit those 2 s's. Even though we're going farther, we only have 2 of those 2s squares to go through, because after that, on our way to nitrogen, the rest of those elements, the rest of this square over here, are the 2 p's. So we've got our 2 p's that we're running into next, and in order to get to nitrogen's square, we want to go 3 squares in. Don't stop at boron or carbon. We have to go 3 squares in to get to nitrogen. For magnesium, which is down on the third row, planning this out, I've got to go across the whole first row and the whole second row, and then we go a little bit farther to get to magnesium. So that whole first row is taken up by 1s2. That second row starts with 2s, go 2 squares in, and then we've got to remember we're still jumping over the 2 p's. We have to finish that second row before we can get to the third row. And if we're trying to go through all of these p's, if you count them, there are 1, 2, 3, 4, 5, 6 blocks, 6 squares to go through here. And we got to go through all of them in order to get to the end of the second row. So 2p6. And after the second row, we're not quite there yet. Magnesium's on the third row, so that's 3s to start with. And since it is 2 spaces in, that's 3s2. Iron is a little bit farther down. It's in that fourth row, which means we're going to have to go even farther. Finish the third row, and then go a couple of spaces over in that fourth row. So I'm going to do those first 2 rows for you. This is getting pretty repetitive. 1s2, 2s2, 2p6. That's gotten us through the entire second row, first and second. Where do we go once we're done with the second row? To the third row. We do have to go 2 squares in to get through those 3 s's, but then we've got to keep going, finish out that third row with all 6 of those 3 p's. That gets us to the end of the third row. Where do we go next? Beginning of the fourth row. It's the 4 s's. There's only 2 4s's there. They're right up against those Ds, but those are completely different. So that's going to be 4s2. And then the next thing we hit are those 3 Ds, and that's where iron is. It's 1, 2, 3, 4, 5, 6. 3, 4, 5. It's supposed to be 6 spaces in. Let me double check. Yes, it is. After counting on my periodic table where I can see those symbols, my little blue square was off by 1. But if we count that, that is 6 squares in. So that's 3d6. Now don't worry too much about the fact that this 3d came after the 4s. That's just the way the periodic table is put together. Remember, our s's start at 1, our p's start at 2, d's start at 3, and f's start at 4. It's weird, but we just keep going across row by row, labeling what we hit and how far we go, and just trust the chemistry that there's a reason for it. There's some quantum mechanics reasons we can talk about if you want to take AP Chem, but it's nothing you need to worry about in honors chem. Just follow the periodic table and those labels row by row till you get to your element. Now, gold is all the way down here, AU. So this is going to be kind of a long one, but we just need to go, even though that's down in the 6th row, we're going to take it row by row. 1st row, 2nd row, 3rd row, 4th row, 5th row, and then most of the way across the 6th row. What I want to remind you about now is that when we get down to the 6th row, between the 6s and the 5d, we have to go through that 4f. And it is only going to be the 4f because that 6th row only lines up with the 4f. We don't have to go through the 4f and the 5f. We just go through one row of each letter as we go across the periodic table. It's just that those f's line up with those bottom 2 rows of our s's and d's. So we've got to remember where that bold line is like all of those f's squeezed into that one bold line. So we've got to go through all of them, and there are 14 of them when we get down there. So we just can't forget about those specific elements. So just like before, I'm going to get you through those first 2 rows without having to kind of walk you through it. 1s2, 2s2, 2p6. After the end of that 2nd row, we go to the beginning of the 3rd row. Go 2 squares into those s's. Then we have to finish out that 3rd row. Go over to the 3 p's. Go through all 6 of them. Then our 4th row. Start it. Go through both of those 4s squares. Then down into the 3Ds. If we're going through all of them, because we need to finish this whole row, there are 10 squares there if we count them. We're still not done with that 4th row. We got to get through those 4 Ps. There are 6 of them. Then down to that 5th row, 5s. Go 2 spaces. Then down into the 4Ds. Go through all 10 of them. Finish out the 5th row with the 5 Ps, all 6 of them. We're almost there. 6th row starts with 6s. Go 2 spaces. And this is where we've got to remember that we need to go through our f's, or really just the 4f. And there are 14 of them if we're going through all of them. And then we can finish up in the 5Ds. And in order to get to gold, we're not going through all 10 of them. We have to go through 9, stopping at the 2nd to last space. So I know it's a long configuration, and I barely managed to make it fit on my line. I hope that you fit it all in on that page. But it's just a systematic process of going through row by row until we get to the element square that we've got. Now, I know I say optional complete ND's configuration. Really, it's going to be basically the same as gold's until we get through that kind of 6th energy level there, because ND is down here in the F's, and a lot of people think that that's even harder because it's the F block, but we already went through the F's. So if we wanted to stop in the F's, we'd have to go 6S2, but then we just go 4F, 1, 2, 3, 4, and then we're there. It's actually shorter than gold because we didn't have to go through all of the F's and then the D's. So don't let the F's freak you out. They are a little weird and different, but they're not that freaky. Now, the practice problems that go along with this are page 11 and 12, part A. That's what we call the complete electron configuration. It starts at 1s and completely labels every electron in every orbital. I'm going to teach you about B and C next. You can also do a little bit of page 13, where it's starting to have you use a configuration to find an element. You can also start looking at some of these configurations and fixing some of the issues. 3 out of the 4 of these have issues, and you can only really look at this first one for now, but I'll remind you of that later once we can finish these out. This is just like what we wrote at the bottom of page 7. What do each of these parts of our configuration mean? It's not really the area of the periodic table. It's not really the number of squares. It's telling us something about the atom. So go back, check page 7 if you need that there. Then 13 and 14 might be a little bit of a stretch if you're just starting this. You can come back to this later. But what happens with 13 and 14 is you're starting to do some analysis on some of these configurations. So even though it doesn't say write out the configuration for these elements, that's really what you're going to need to do so you can look at it and analyze it. So let me give you 2 examples here. In 13, we're asking you how many electrons are in p orbitals for the following elements. Well, you need to write out the configuration for these elements. Here I've done chlorine for you. And then you need to look at which terms have p's in them. And remember that the exponent number on those p's and every letter tells us the number of electrons in those orbitals. So here, because I have some 2p electrons and 3p electrons, if we add those together, that tells us that chlorine has 11 total electrons in different, various energy levels of these peanut-shaped orbitals. We do the same thing when it's asking about our 4th energy level electrons. It's just that the energy level is the big number before the letter. So we look for all of the terms that have 4s in them, and then we add up the electrons in those orbitals. This is 2 plus 1. It means that gallium has 3 4th energy level electrons. So use your configuration as a guide. Write those out if you have the space on the paper, or write them out on a separate sheet of paper, and look for the p's or the 4s in order to add up the total number of electrons. We can do the rest of these problems in page 14 stuff once we learn some more configurations.